In this video, we're going to go over Chapter 3, which focuses on similarity in triangles and in polygons. So on the opening slide, I pretty much have a summary of all the things that are in this chapter. So here's some information about similarity. Here's some ways of proving similarity. Here are some similar shapes. Then we move into right-angled trig. And we have Pythagorean theorem here. We have the converse of Pythagorean theorem here. We have SOHCAHTOA, which is ways of using trig to solve for missing parts of triangles. And then we have the law of sines and law of cosines, which you can also use with right-angle trig, but you can use to solve for parts of missing triangles when the triangles are not right angles. So that's a summary of what we'll be doing. So let's start doing each one. Okay, in the previous chapter, Chapter 2, we talked about congruent triangles, and we said that congruent triangles have all the same side lengths and all the same angles. Okay, so another category of triangles or of polygons is similar polygons or similar triangles. So here's an example of two similar triangles. So similar triangles look similar, meaning they look like they have the same shape, okay? But they don't have all the same side lengths. They have the same angle lengths. So the angles are all congruent, okay? So the corresponding angles are congruent. So for example, angle A and angle D have one little arch marking their shape, so those values are equal. Angle B and angle E have equal angles, and angle C and angle F have equal angles. This is called a similarity statement, and you can see that the way the similarity statement is set up, A equals D, B equals E, and C equals F, which is exactly what we just went through. Okay, so that's with regards to the angles in a similar triangle situation. What about their sides? We said they were not congruent, so what are they? Well, corresponding sides are in proportion. So they all have what's called the same scale factor. So let's look at this. I'm going to erase what I have written over here so we can see the similarity statement again, because it's going to help us figure out the proportions to the sides. So looking at this similarity statement, and maybe I'll change colors. So piece or segment AB is going to be proportional to DE. So where is AB? AB is here, and here is DE. So that proportion is 6 is to 9. Okay, so then let me change colors again. And BC will be in proportion to EF. So here's BC, here is EF. So 6/9 should have the same proportion as 4/6. And then we'll change color one last time. And we'll say CA is right here, is proportional to FD. So FD is here. So is that true? And I'm going to try to squeeze this here. Is it true that 3 is to 4.5? So if you put this in your calculator, you should get the same fractional equivalent for all three of these. And trying to put it in reduced terms, my fraction that represents the scale factor is 2/3. If you put each of these in your graphing calculator, just in your plain, division mode, you would get a decimal of 0.667. So they all have the same scale factor, and scale factor is generally written as a fraction in simplest terms. So What I generally will ask you to do with these problems, so let me erase something else here. I'm going to get rid of this for a second, but you can go back earlier if you need that explanation read to you again. I will ask you to do things like give me the list of the congruent angles. So the congruent angles you could get from the similarity statement, which is usually wise. Just in case it's confusing with the orientation of each triangle, you can always line things up using the similarity statement. So from the similarity statement, I can see that angle A equals angle D, and angle B equals angle E, and angle C equals angle F. Okay, so that's one thing I'm going to ask you about these. The second thing is give me the list of the proportional sides. So again, using the similarity statement, AB, using letters to name the sides, is to DE, just like BC is to EF, just like CA is to FD. Okay, so those are the proportional sides written as fractions set equal to one another. The blue mark the angles. And the other important thing to understand is how to get the scale factor. You get the scale factor by taking one of the proportions and reducing it to simplest terms. Okay, so that's a good overview of similar triangles. Okay, so we're going to go through 3 different theorems. So if asked to prove that you have 2 triangles, so this is our focus on triangles, proving that 2 triangles are similar, you can prove it by AA, SAS, or SSS. And we're going to go through each of these on the next 3 slides. Okay, so proving AA means if you can find 2 angles that are identical between the 2 triangles, then those 2 triangles must be similar. Okay, so in this case, I see that angle B equals angle Z, and then I also see that angle A equals angle Y. So because I can see I have 2 pairs of corresponding angles, and I can see that by their markings, I know that I actually have 3 equal angles because the sum of the angles inside a triangle must be 180. So if these 2 add to the same if ZY adds to the same sum as does BA, then angle C has to equal angle X. And we know that when we have similar triangles, all the angles are congruent. Okay, so we can prove by AA that we have similar shapes. So let's write a similarity statement based on this sketch. So I'll change color. And my similarity statement would be, in the first triangle, I'm going to list it as triangle BAC is similar. Okay, what angle equals B? You should be saying Z. What angle equals A? You should be saying Y. And then what angle do we talk about having to equal C? And that's X. So this order is very important. You have to be able to line up congruent angles through your similarity statement. Okay, and we can indeed do that through this similarity statement. Okay, so that's one of the theorems you can use for proving that things are similar. So let's go on to the next slide and we'll do a second theorem. Okay, this theorem is side-angle-side similarity theorem. So what does that mean? So that means in 2 triangles, well, let's read this together. If 2 triangles have 2 pairs of corresponding sides in the same ratio, and if the included angle determined by the pairs of sides are congruent, then the sides are similar. So let's look at this. Here are congruent angles. So that angle is sandwiched between these sides. So you have to have side, angle, side, and the sides are the bread and the angle is the jelly. So think of it like that. Okay? We cannot use angle side AC in this, because side AC is not part of the sandwich. Neither is side DE. So those are no's in terms of proving by side, angle, side. So I'm going to say side, angle, side. In order to prove it, I have to have congruent angles. I have those. They're both 50. Okay, so then look at these two numbers. So let me change color. So look at these two numbers, 12 and 24, and 8 and 16. So take the two smaller numbers from each triangle. So I'm going to say, reading from the left to the right, 12 is to 8, just like 24 is to 16. So is that true? Well, I can see right away, if I reduce this, I get 12 over 8. So yes, I don't need the question mark. I have sides that are indeed in ratio, have the same ratio. So therefore, I can prove that these two triangles are similar, okay, not congruent, but similar, by side, angle, side. Okay, so now let's write a similarity statement. So you've got to use what you have. Why don't we start with the angle that we were given. So angle B here. Now watch what I'm going to do. I'm going to put angle F here. That's the first angle I'm going to deal with. Then go down the side of the smallest side for the first triangle. I would go from B to A. Going down the smaller of the two sides in the second triangle, I go from F to D. Then what's remaining? The remaining letter is C for the left triangle, and the remaining letter is E for the right triangle. That is my similarity statement. Okay, so you want to know how to create those when given a proof by side, angle, side. Okay, let's do side, side, side on the next slide. Okay, so here's the last one. Look at the two triangles that you have been given. Because you have been given no angles whatsoever, the only way you can prove similarity is through comparing the sides. The sides have to be in proportion. So to figure out if you indeed have sides that all share the same proportion, reading from the left to the right, find the smallest number, or find the smallest length side. It's 14 here, and it is 10 here. So 14 is to 10, just like, what's the next biggest size? 21 here and 15 here. Just like 21 is to 15, and then pick your last ones. And that's just like 28 is to 20. 28 is to 20. So what can you do here? You have some options. You could go ahead and reduce them so that you have it in simplest form, but probably the quickest way to figure out if you have similarity is to get the decimal equivalent. So 14 divided by 10 is 1.4, 21 divided by 15, 1.4, 28 divided by 20, 1.4. So now that I know that these are all equal, because I've just checked this out with my calculator, go ahead and get your scale factor, because your scale factor is the proportion in simplest form. So I think it's probably easiest to reduce the 14 over 10. So 2 goes into 14 7 times, and 2 goes into 10 5 times. That is going to be my scale factor. Okay, so we've proven by SSS that we have similar triangles. Now let's go ahead and we're going to write down what the similarity statement would be. Okay, so it's a little bit trickier here. Why don't we find the side that is the smallest? Okay, so, and I'm going to start at the letter that's in between the smallest and the biggest. So C is the letter that's in between the smallest and the biggest on the triangle to the left. Okay, and D is that same angle for the triangle to the right. Okay, so go from C, let's go down the small side. I go to A. Go from D, go down the small side. I go to E. Okay, from A, C, A, I'm going to finish the triangle with a B. D, E, I'm going to finish the triangle with an F. That is my similarity statement. So you need to be very careful how you get that. It's always easier if you have angles to deal with, but as long as you take some time to agree in your head upon a starting point, and I started between the big and the small, and picked C, then I picked D, and that's where I began my similarity statement. Okay, so now that we have these 3 theorems covered, we're going to go ahead and do some more practice with similarity. Okay, so this slide, as promised, says practice with similarity. Let's read it together. Solve for the missing side. So what's the missing side? It looks like its value x using similarity. So it says, first figure out why the inside triangle and the large triangle are similar. Then work on the scale factor. Also, you may find this easier if you draw the 2 triangles separately. So we will indeed do that. So first off, why are these 2 triangles similar? Well, that's kind of an interesting thought. So they are similar. I'm going to tell you they have a common angle here. And then what's happening is, you don't know this yet, but I will tell you, give you a little heads up, this angle is going to be equal to this angle because they are corresponding angles. So when I take that back, we covered this in the last chapter. Do you see how these lines are parallel right here and continuing? Parallel lines being crossed by a transversal. This angle, the bottom of the big triangle, this angle, the bottom of the large triangle, or the small triangle, they are identical because they're corresponding angles. So therefore, in addition to having a common angle here, you have 2 other angles, and so therefore you can prove by angle that this big triangle and the little triangle are indeed similar. So then I say it may be easier to draw these separately, so I'm going to do exactly that. Here's your small triangle, and its measurements are x and 6. Okay, then we're going to draw the big triangle. Here's the bigger triangle, drawing it in the same orientation as what I'm seeing, only pulling it out, and its values very carefully are x plus 1, do you see why? And 8. All right, so we have a problem here, or we have a good problem to work on. So what do I know? I know that these 2 triangles are similar. If they're similar, then I have corresponding sides in proportion. So let's set that up. So here's your proportionality. You can say x is to x plus 1, just like 6 is to 8. So if you have fraction equal to fraction, you are going to do your cross products. So there's what you're going to do. You're going to multiply like that. When we do that, we get 6 times x plus 6, do you see that? I'm distributing, equals 8x. Okay, bring your x's on one side, and I get 6 equals 2x, divide by 2, and I end up getting x equals 3. Okay, so let's check our answer. So far I'm getting x is 3. If I plug in 3 here for x, I'm going to plug in 4 here. Does it work? Is it true that 3 is to 4 just like 6 is to x? Yes, that works. So now I know that having a solution of x equals 3 is the correct answer for that missing side length. Okay, you may want to look over that again, but that's a nice, neat problem. Okay, in this slide, we're going to talk about another application of similar triangles. Very common problems are called shadow problems, and they're called shadow problems because they talk about a light shining on something and casting a shadow, and that creates similar triangles. So I put this little note up here, and I said, note, triangles built from shadows are similar due to angle. One angle is the angle of the sun, and the other angle, or could be sun or street lamp, and the other angle is the angle with the ground, and that angle is always a right angle. So you've got two angles in common. That creates similar triangles. Okay, also I want to note that there is a worksheet on applications using similar triangles, and it's key. I put it up on Joule for you for day 3. You should print that out and practice that. We're going to go through the basics of these shadow problems here, and then you're going to practice additionally on your own. Okay, so this problem says a girl who's 161 centimeters tall. So here's the girl right here on this line. She stands 360 centimeters from a lamp post. Okay, so you're getting the light from a lamp post. Her shadow from the light. Okay, so let me just do this. When she casts the shadow, so here's the girl's shadow. Okay, so her shadow from the light is 90 centimeters long. So that's her shadow length. How high is the lamppost? Okay, so let's think about this. Can I see that I have similar triangles? So how do I know that? Okay, I know it for the following reason. So let's label this so that we can see our similarity first so we understand the concept. Okay, you may assume that this lamppost is straight up and down at a 90 degree to the ground. You may assume the same thing about this little girl standing up. That's one angle you have in common. Okay, so that's one of them. Second angle. This is the angle that the lamppost makes, the light makes with the ground. Okay, the lamppost shines, so here's the little shining. It shines and hits the ground at that angle. When it gets to the girl, it hits the ground at the same angle. So that's your second angle that you have in common. Then you actually have a third angle in common. What's the third angle that you have in common? Well, this toe angle. They both share the same toe angle. So you actually have angle similarity a couple of ways. So do you see, so I'm going to draw this separately for a sec. Do you see that you really have two triangles here? You have this triangle that has the little girl. Okay, so this is the little girl. And then you have a second triangle. Okay, the second triangle has the lamp post. So here's the little lamp post with the light. Okay, so that's a lamp post. And you have those two triangles, and we have some measurements. So we know, for example, that this shadow is 90, and we know that her height is 160. We know the whole length of the shadow cast by the lamppost. That is 90 plus 360. So you've got it in your calculator or in your head, say 90 plus 360, and you should be getting 450. So this length is 450, and we don't know this. Okay, this is our x. And what we've established by angle is that these two triangles are similar. So set up your proportions. So we'll change one last time. Setting up my proportions, I would say that 90 is to 450 just like 160 is to x. Okay, do your cross products, and I get 90x equals, okay, 160 times 450 is 72000. Divide both sides by 90. Okay, so that's 7200 divided by 9, and I'm getting x is 800. And if they gave me feet or meters or centimeters, I had to give them back the units. Everything was in centimeters. This lamppost is 800 centimeters, and that's how I use similarity to answer shadow problems. Okay, if you find it easier to write the problem as two separate triangles, go ahead and do that. If you find it just as easy to keep it as one, and you can still get your proportions, these are your proportions successfully, that's fine as well. Okay, so that's how you do that. The similarity triangle worksheet will give you additional practice on this important concept. Okay, in this slide, we extend the thought of similarity onto altitudes, and I've cut off a little bit, but I hope we can still talk about it. I think we can still read it. So it says definition of an altitude. So first off, you need to know that an altitude is when you drop a vertical line from a vertex to the opposite side and it forms a right angle. That is called an altitude. So here is an altitude. See the right angle formed? Here is an altitude. And in an obtuse triangle, the altitude will be outside the triangle. So isosceles, altitude's inside. Right triangle, the altitude will be one of the legs. And an obtuse triangle, the altitude will be outside. Okay, so that's facts about altitude. So you need to know things about altitude just in general. Okay, then the next piece of it as it relates to similarity is that if two triangles are similar, then their scale factor between their sides also extends to their altitude. Okay, so that means here's two triangles, and I'm going to tell you that they are similar. Here's an altitude 20, here's an altitude 10. If you want to make an attempt to get x, you're going to do your ratios. Okay, so let's set up our proportions since we know that you can treat an altitude in the same exact way that you treat a side. So I'm going to say 22, that's the side length, is to x, which is the missing side length, just like 20, which is the altitude, is to 10. Okay, so you're going to do your cross products, and I can see right away that that's x is going to be 11. But let's say you didn't see that. Doing your cross products, I'll do it over here to the left, 20x equals 220. Divide by 20, divide by 20, and you're getting x equals 11. So you can use your similarity ratios, your proportions, your scale factor, any way you want to call it, to solve for a missing side when giving information about an altitude. Once you know these triangles are similar, you are able to set up these proportions. Okay, so let's go on, and we have a little bit more information about right triangles on the next slide. Because so far we've been dealing with all kinds of triangles. We're going to specify and focus on right triangles. Okay, so this is pronounced Pythagorean. Okay, Pythagorean theorem. So it pertains only to right triangles in its purest form, and I'll explain that later. Okay, so the theorem is if triangle ABC, so let's make sure that we understand how to label this. So I'm going to do this as an aside. If this is side A, its opposite angle A. Notice it's small letter for the side, capital letter for the angle. Side B is opposite angle B. Side C is opposite angle C. Okay, so that's the normal way we label triangles. So it just so happens, and it frequently happens, and the formula is geared towards the fact that C is a right angle. So there's a relationship between these sides. So let's go back to the theorem. If triangle ABC is a triangle with a right angle at C, then the square of side A plus the square of side B equals the square of side C. So that is this formula. Okay, so notice that you have small letters. You have small letters because that's pertaining to the sides. Okay, so if I know I have a right triangle, I can solve for a missing side by using this formula. So let's talk about that for a second. So what if I said, I'm just going to keep everything in terms of variables right now, but what if I said I would like to find out the length of A in terms of B and C? So what I would do is I'd subtract B squared from both sides, and I would say that A squared equals C squared minus B squared. I would then take the square root of both sides, and I would say that A equals the square root of C squared minus B squared. Now that you're going to use that same approach if you have numbers, or I should say when you have numbers. Okay, so that's Pythagorean theorem, using it to solve for a missing side. Okay, you don't use it to solve for missing angles, you use it to solve for missing sides. Okay, so this here is a link to an activity that's a discovery activity for Pythagorean theorem. It is very good. It is very good for upper middle school students because it's a nice exploration. So I posted this activity on Joule for you. It's not a requirement that you do it. However, I would think that you may want to print it out and at least give it a good look and see if it helps you understand Pythagorean theorem, and if you can perhaps see a way to apply this to your class. Okay, so let's go on. We're going to discuss the converse of the Pythagorean theorem in just a second on the next slide. So this will be our last slide for this chapter, this part 1 of the video, and then I'll continue the video on I'll continue working on this PowerPoint in another video, but I wanted to conclude with using the converse of the Pythagorean theorem. So we know already that this first checkbox is true when I have a right angle. Well, what if I give you the measurements of a triangle and I don't tell you whether it's a right angle, a right triangle or not? Is there any way you can use Pythagorean theorem to figure out whether you have a right triangle? And the answer is yes. Okay, so this is the deal. The side that is your C is always going to be the largest. Okay, so if you always pick that to be your largest, you can check out this relationship. So let's say I'm given a triangle. So I'm going to draw a triangle. Why don't I just, I'm just going to tell you, I'll tell you that a triangle has the following 3 sides. So let's just say that my triangle has sides 3, 4, and 7. And I want to know whether that is a right triangle, an acute triangle, which means it has all acute angles, or an obtuse triangle, which means it has one angle larger than 90. So what I do is I take the 2 smallest sides, which are 3 and 4, and I square them. So 3 squared plus 4 squared. Instead of saying equals, I'm going to put a big old question mark here. Then I'm going to say 7 squared. So 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. So 25 is here. 7 squared is 49. 49 is there. So 49 is greater than 25. Okay? So since it's greater than 25, this is what's happening. I have an obtuse triangle. So how do you remember this? Well, do you see how the less than symbol, if you say 25 is less than 49, read it that way. The less than symbol is pointing to the B. And what letter is in obtuse? B. If you have a less than, it is an obtuse triangle. Okay, what if I have a greater than? If I have a greater than, then the arrow, if you will, is pointing to the C. What letter is in acute? That would be C. So if you find that a squared plus b squared is greater than c squared, then the angle is acute. Excuse me. Okay, let's try this. What if I tell you the sides of a triangle are 5, 5, and 6? Okay, so 5, 5, and 6. So what do we have? The 5 and the 5 are clearly the smaller of the sides. So that's 25. 25 plus another 25. And then question mark, 6 squared is 36. So 25 and 25 is 50. So 50 is greater than 36. Greater means that I have this second scenario, and therefore I have an acute angle. Okay, a word about these triples. These triples are all going to be right triangles. So we can try any one of these and it'll satisfy the equation a squared plus b squared equals c squared. So let's just try this one just for ease. So the two smaller numbers, 3 squared plus 4 squared, question mark, 5 squared. We already did 3 squared plus 4 squared. We know that's 25. Well, 5 squared is also 25, so therefore it equals it. Since a squared plus b squared equals c squared, I have a right triangle. Okay, so that's the converse of the Pythagorean theorem. It allows us to use our sides to determine whether we have a right triangle, an acute triangle, or an obtuse triangle. So that should be helpful to you. Okay, here's your general scenario of a right triangle, what it looks like, where the 90 degree is, where the hypotenuse is. Okay, so there you're all set. So we're going to stop this video and I'll continue the rest of the slides on a second video.